What if you woke up one morning to the announcement that humanity had just taken its first step toward the stars? Picture the headlines: breaking news that a spacecraft, built by human hands, had crossed the unimaginable gulf between our solar system and another. The idea isn't just science fiction anymore. For centuries, interstellar travel lived only in our dreams, whispered in myths and sketched in the margins of astronomers' notebooks. But today, that dream is closer to reality than ever before, and the theories about how it might happen, they're even wilder than you think. We're standing at the edge of a cosmic frontier, staring into the abyss of space, wondering not if we'll reach another star, but when and how. Some of the brightest minds on Earth have spent decades wrestling with this challenge, spinning out ideas that sound like they're ripped straight from a futuristic novel. Warp drives bending the fabric of space-time, generation ships carrying entire civilizations across the void, nanoprobes light as a feather surfing laser beams to distant worlds. These aren't just fantasies, they're real, serious theories, each with its own tantalizing promise and heart-stopping risks. And buried in them lies something even more profound: the story of humanity's restless drive to explore, to push beyond the known, no matter how impossible it seems. That's what we're diving into today. 30 theories, 30 glimpses into how we might one day crack the code of interstellar travel. Some will sound eerily plausible. Others will stretch your imagination to its limits, but all of them will make you realize something extraordinary. We're living in the era where the first steps are being taken. The names of those who finally cross that cosmic threshold might not even be born yet, but the ideas, they're already here, waiting for us to uncover them. So buckle up. This isn't just a journey through space, it's a journey through the outer edges of human ingenuity, where science and speculation collide in the most thrilling ways imaginable. And by the end, you'll never look at the night sky the same way again. What if we're not the first to dream of crossing the stars? Before we even ignited our first rockets, could another civilization have already cracked the code of interstellar travel? This is the spine-tingling premise behind the ancient alien exodus theory, the idea that somewhere in the vastness of space, a species far older and more advanced than ours might have once sailed between the stars, leaving behind faint traces of their journey. Think about the pyramids, not the ones on Earth, but the hypothetical ruins on distant exoplanets, buried under layers of cosmic dust waiting to be found. The Fermi Paradox looms large here. If the universe is so unimaginably vast with billions of habitable planets, why haven't we seen any evidence of alien civilizations? The ancient alien exodus offers one chilling answer. Maybe we just missed them. Maybe they rose, explored, and vanished long before humans even walked the Earth. Some theorists suggest these pioneers could have left behind dormant probes, derelict megastructures, or even encoded messages in the very fabric of space itself, clues hidden in plain sight like cosmic breadcrumbs. Take the mysterious Oumuamua, that strange interstellar object that zipped through our solar system in 2017. Its odd shape and unexpected acceleration had even serious scientists whispering about artificial origins. While most evidence points to natural causes, the thrill of the unknown remains. What if the next unusual object we spot isn't a rogue asteroid, but a relic from a long-dead starfaring race? Then there's the haunting idea of paleocontact, the notion that ancient aliens might have visited Earth itself, leaving behind myths and legends that we now dismiss as mere stories. The Dogon people of West Africa, for instance, knew details about Sirius B, a star invisible to the naked eye, centuries before telescopes confirmed its existence. Coincidence, or could it be a fragment of long-lost knowledge passed down from interstellar visitors? But here's the twist. If an ancient civilization did achieve interstellar travel, why is the galaxy so quiet? One possibility is Grimm the Great Filter. maybe every advanced species hits a wall, a technological or biological catastrophe that wipes them out before they can spread far. Or perhaps they evolved beyond our comprehension, leaving physical travel behind for something we can't yet imagine. Either way, the ancient alien exodus theory forces us to confront a humbling thought. We might not be the pioneers we imagine ourselves to be, but latecomers to a cosmic stage where the curtains fell long ago. And if that's true, the most important question isn't where they went, but whether their fate could one day be ours. The WOW signal still haunts astronomers decades after that blistering summer night in 1977. For 72 electrifying seconds, a radio telescope in Ohio picked up a signal so powerful, so unnervingly artificial in pattern, that the astronomer who discovered it scrawled, "Wow," in red ink on the printout, and the name stuck. It came from the direction of the Sagittarius constellation, matching the predicted signature of an interstellar transmission. Then, just as suddenly as it appeared, it vanished, never to repeat. Was it our first brush with an alien beacon, a fleeting hello from across the void, or something far more mundane, a passing satellite, a glitch, or even a comet's hydrogen cloud reflecting radio waves in just the right way? The debate still rages because the WOW signal embodies the tantalizing razor's edge between discovery and dead end. Then there's Oumuamua, the interstellar interloper that defied easy explanation. When this sleek, tumbling object raced past the sun in 2017, scientists scrambled to categorize it. Its elongated shape, lack of a comet's telltale tail, and most puzzling, its slight but measurable acceleration as it departed left even seasoned researchers grasping for answers. Harvard astrophysicist Avi Loeb famously floated the possibility of artificial origin, suggesting it might be a light sail fragment from an alien civilization. The mainstream scientific pushback was swift, outgassing from hidden ices, thermal radiation pressure, or other natural phenomena could explain its behavior. But the sheer novelty of Oumuamua forces us to confront an uncomfortable truth sometimes. The universe throws curveballs that challenge our certainty. Skeptics rightly caution against jumping to extraterrestrial conclusions. The history of astronomy is littered with alien signals later debunked, like pulsars, whose clockwork radio bursts were once seriously considered evidence of alien beacons until the discovery of spinning neutron stars. The null hypothesis remains our sturdiest tool. Extraordinary claims demand extraordinary evidence. Yet buried in these mysteries lies a deeper lesson about how science grapples with the unknown. The WOW signal and Oumuamua aren't just footnotes, they're stress tests for our imagination, forcing us to ask what we'd recognize as proof if it ever stared back at us from the cosmos. Perhaps the most sobering takeaway is how fragile interstellar evidence can be. A signal fades, an object streaks away into darkness without repeat observations or physical samples. Even the most tantalizing clues crumble into dust. This is why projects like Breakthrough Listen or the upcoming Vera Rubin Observatory are so vital. They're our nets cast wide, hoping to catch the next anomaly before it slips through our fingers. Because if ancient aliens did leave breadcrumbs across the galaxy, finding them won't just take luck. It'll take patience, precision, and the humility to admit that some answers might elude us until the stars themselves decide to whisper back. Imagine a city floating in the blackness of space, not a sleek starship darting between worlds, but a vast, slow-moving world of its own, carrying not just explorers but entire generations destined to live and die in transit. This is the staggering vision behind generation ships, colossal arcs designed to bridge the impossible distances between stars over centuries or even millennia. Unlike warp drives or wormholes, this theory doesn't rely on undiscovered physics, just sheer human endurance. The math is brutally simple. Even our closest stellar neighbor, Proxima Centauri, is over 4 light-years away. With current propulsion, that's a journey lasting tens of thousands of years. But scale up the ship, think a spinning habitat with artificial gravity, closed-loop ecosystems, and populations in the tens of thousands, and suddenly, the voyage becomes a question of sociology as much as engineering. Could a society stay stable for 500 years, 1,000? Would the original mission's purpose survive when those arriving at the destination are the distant descendants of those who launched it? History offers sobering parallels. Isolated communities on Earth, from the Polynesian voyagers to the doomed settlers of Roanoke, show how quickly social order can unravel without careful planning. On a generation ship, rebellion isn't just a risk, it's existential. A single uprising over resource allocation could doom everyone aboard. That's why theorists obsess over governance models. Would a rigid hierarchy prevent chaos or breed resentment? Could AI overseers enforce fairness, or would they become tyrannical? And what happens when cultural memory of Earth fades into myth? Then there's the biological challenge. Genetic diversity would need meticulous management to avoid inbreeding over centuries. Early studies like Biosphere 2 demonstrated how fragile closed ecosystems can be when oxygen levels plummeted unexpectedly. It nearly ended the experiment. Scale that to a starship, and a single crop failure or oxygen leak could mean extinction. Some proposals suggest sending multiple arcs in convoy as insurance, but that multiplies the cost and complexity. Yet for all its hurdles, the generation ship concept has one irresistible advantage. It requires no scientific miracles. Every technology needed, from hydroponics to nuclear reactors, either exists or is within projected reach. Projects like the JPL's Advanced Life Support Systems already test closed-loop agriculture, while Mars habitat simulations stress-test human psychology in isolation. The real barrier may not be engineering, but willpower. Would any civilization commit to a project where the architects won't live to see the first progress reports, let alone the destination? Perhaps the most haunting question isn't whether we could build such a ship, but whether its passengers would still care about Earth by journey's end. Would they gaze at Proxima Centauri's planets with wonder or resentment for the ancestors who consigned them to a metal womb? In that tension lies the generation ship's paradox. It's the most plausible path to the stars, and the one that demands the most from our humanity. Modern proposals for generation ships read like blueprints from a sci-fi epic, except they're dead serious. Take Project Daedalus, the British Interplanetary Society's brainchild from the 1970s. This conceptual interstellar probe was designed to reach Barnard's star in just 50 years using nuclear pulse propulsion, essentially detonating atomic bombs behind the ship to push it forward. While Daedalus was unmanned, its successor, Project Icarus, reimagined the concept with updated tech, reigniting debates about whether such a vessel could sustain human life for centuries. The numbers alone are staggering. A ship the size of a skyscraper carrying thousands, with reactors burning deuterium and helium-3 mined from lunar soil or gas giants. It's engineering on a scale that makes the International Space Station look like a backyard shed. But for all their technical audacity, these designs pale next to the ethical quagmires they unearth. Who gets a seat on the Ark? Selection criteria could spark global conflict. Would we prioritize genetic diversity, skills, or some cold algorithm optimizing survival odds? And what about the unborn generations destined to live and die in transit, never knowing Earth except as a fading legend? Philosophers like Robert Sparrow argue that launching a generation ship without the consent of those born en route is a moral violation, akin to sentencing innocents to life imprisonment in a metal cocoon. Others counter that exploration has always involved sacrifice, from Polynesian navigators to Antarctic pioneers, except here, the stakes span millennia. Then there's the bottle world problem. Even with flawless engineering, a generation ship's closed ecosystem would drift culturally and biologically over time. Languages mutate within decades in isolation. Imagine the linguistic chasm after 500 years. Customs could distort beyond recognition, turning the mission's purpose into myth. Some theorists propose cultural time capsules or AI historians to preserve Earth's knowledge, but that assumes future crews would care. The generation ship's greatest threat might not be asteroid collisions or system failures, but sheer existential apathy, a crew that forgets why they're out there. Yet amid these sobering challenges, glimmers of innovation emerge. NASA's Hermes project explores electromagnetic propulsion that could slash travel times, while breakthroughs in CRISPR gene editing might one day let us engineer crops or even humans for deep space resilience. The private sector isn't waiting either. Initiatives like Breakthrough Starshot aim to send nanocraft to Alpha Centauri within a generation, proving that audacious ideas can leap from paper to reality. The irony is crushing. Generation ships demand unprecedented cooperation across generations, yet humanity struggles to plan beyond election cycles. Building one would require a civilization mature enough to invest in a future it won't see, a test not of technology, but of our species' ability to think beyond itself. Maybe that's the real bottleneck, not the physics of star travel, but the fragility of human foresight. So before we sketch the next Daedalus, perhaps we should ask, are we ready to become the kind of civilization that deserves to reach the stars? What if everything we know about interstellar travel is wrong? What if instead of crossing the vast emptiness between stars, we could simply step through a cosmic doorway, arriving at our destination in the blink of an eye? This is the mind-bending promise of wormholes, tunnels through the very fabric of space-time, where distances that would take millennia to cross become nothing more than a short stroll. The math behind wormholes traces back to Einstein and his colleague Nathan Rosen in 1935. Their equations suggested the possibility of bridges connecting distant points in spacetime, structures we now call Einstein-Rosen bridges. Picture spacetime as a sheet of paper folded so two distant points touch. A wormhole would be like poking a pencil through that fold, creating a shortcut between places that should be impossibly far apart. The implications are staggering. A trip to Alpha Centauri wouldn't take decades, it could take seconds. But here's the catch. While wormholes are mathematically sound, they're cosmically elusive. No one's ever observed one, and the conditions needed to create or stabilize them sound like something from a physicist's wildest dreams. You'd need what scientists call exotic matter, a substance with negative energy density to prop open the wormhole's throat and prevent it from collapsing the instant it forms. This isn't just rare, it might not even exist in nature. Some theories suggest quantum effects could produce tiny amounts of it, but scaling that up to fit a starship. That's a challenge even our boldest engineers haven't cracked. And then there's the stability problem. Even if you could open a wormhole, keeping it stable while something passes through is like trying to hold open a doorway made of quicksand. The slightest disturbance, a single photon out of place, could trigger a catastrophic collapse, crushing anything inside. Some models suggest that advanced civilizations might find ways to reinforce these structures, perhaps using incomprehensibly dense energy fields or manipulating spacetime itself. But for now, these ideas remain firmly in the realm of speculation. Yet despite the hurdles, wormholes captivate us because they defy the crushing inevitability of cosmic distances. They represent a universe where the rules as we know them can be bent, reshaped. Maybe that's why they appear everywhere, from blockbuster films to cutting-edge physics papers. They're more than just a theory, they're a symbol of humanity's refusal to accept limits. After all, if spacetime can fold, who's to say we can't learn to fold it ourselves? The energy needed to pry open a wormhole isn't just enormous, it's almost laughably out of reach with our current understanding of physics. To warp spacetime itself, you'd require energy densities so extreme they border on the absurd. Picture this: some calculations suggest stabilizing a traversable wormhole might demand the equivalent of a star's entire mass converted into pure energy, compressed into a structure smaller than an atom. It's like trying to power New York City for a century with a single AA battery. But the real showstopper isn't just the sheer quantity of energy, it's the type. Wormholes don't just need energy, they crave something far stranger: exotic matter with negative energy density. This isn't your everyday antimatter or dark matter. Exotic matter would have to defy the fundamental rules of general relativity, generating gravitational repulsion instead of attraction. Think of it like cosmic duct tape, holding the wormhole's throat open against the relentless crush of spacetime trying to snap it shut. The catch: no one's ever observed this substance in nature, and laboratory attempts to produce even microscopic amounts are still in their infancy. Recent breakthroughs, though, have sparked cautious optimism. Quantum physics hints at fleeting phenomena like the Casimir effect, where two metal plates in a vacuum can experience a tiny negative energy field between them. It's a far cry from the planetary scale energies needed for a wormhole, but it proves the concept isn't entirely science fiction. Then there's dark energy, the mysterious force accelerating the universe's expansion. Some theorists speculate it might share properties with the exotic matter wormholes require, though extracting or manipulating it remains pure speculation. The challenges don't end there. Even if you could summon enough exotic matter, keeping a wormhole stable while something passes through is like threading a needle during an earthquake. The moment matter or energy enters, the delicate balance could collapse, turning your interstellar shortcut into a catastrophic trap. Some models suggest advanced civilizations might use quantum field manipulation or higher dimensional physics to reinforce the structure, but these ideas are so abstract they're barely testable. Yet here's the twist: the very impossibility of wormholes might be a temporary hurdle. Human history is littered with impossible problems later solved: flight, quantum computing, even the splitting of the atom. The equations say wormholes can exist. Our job is to figure out how to stop them from self-destructing. That's why labs like CERN and projects studying quantum gravity aren't just academic exercises, they're probing the boundaries of what spacetime might allow. So while wormholes remain firmly in the realm of theory, they serve as a thrilling reminder: the universe's rulebook might still have chapters we haven't read. And if we ever crack the code of exotic matter, the stars wouldn't just be distant points of light, they'd be neighbors waiting for us to knock. Imagine a spacecraft with no engines, no fuel tanks, just a wafer-thin sail no thicker than a soap bubble, catching not wind but the pure force of light itself. This is the radical elegance of light sail propulsion, where photons from a laser beam push against a reflective surface, accelerating a probe to speeds once thought impossible. The breakthrough Starshot initiative isn't just testing this idea, it's betting humanity's first interstellar mission on it. Their audacious plan, to fling a fleet of gram-scale microprobes toward Alpha Centauri at 20% the speed of light, reaching our nearest stellar neighbor in just 20 years. At the heart of this concept lies a simple but staggering equation. Light exerts pressure. Though imperceptible in daily life, a powerful enough laser can transfer measurable momentum to an ultra-thin sail. Starshot's design calls for a ground-based laser array, up to 100 gigawatts strong, focused on sails just a few meters across but thinner than a human hair. The lasers would blast for mere minutes, but that burst would propel the probes to a mine bending 60,000 kilometers per second. To put that in perspective, at that speed, you could cross Earth's equator in less than a second. But the engineering hurdles are as immense as the ambition. The sail material must reflect 99.99% of the laser light to avoid vaporizing instantly. Even a speck of dust or a single misaligned photon could destabilize the sail during acceleration. Then there's the challenge of aiming over interstellar distances. Even a laser beam spreads out. Keeping it focused enough to push the probes requires precision beyond anything we've ever attempted. Breakthrough's solution: a phased array of lasers, combining their power like a symphony of light, with adaptive optics adjusting for atmospheric distortion in real time. The probes themselves are marvels of miniaturization, each no larger than a postage stamp, packing cameras, spectrometers, and communication antennas into a package lighter than a paperclip. Power comes from tiny nuclear batteries or even the laser beam itself, bounced back as a data signal. Their job: to scream past Alpha Centauri's planets at breakneck speed, snapping images and collecting data in a fly by lasting mere hours, then beam their findings back across the 4.4 light-year gulf to Earth. Critics point to sobering realities. The laser array would consume energy rivaling small nations, raising questions about cost and practicality. Interstellar dust becomes deadly at these speeds. A grain of sand could shred a probe. And communication across light years requires a receiver as large as a football field just to catch the faint whispers of data. Yet for all the obstacles, Starshot's greatest legacy might be its shift in perspective. Instead of waiting centuries for fusion drives or warp bubbles, it asks, why not leverage the physics we already know to take our first step into the void? The implications ripple far beyond Alpha Centauri. A successful Starshot could pave the way for larger sails carrying heavier payloads, perhaps even future human missions. It's a reminder that sometimes the most revolutionary ideas aren't about inventing new physics, but reimagining how to use the tools already in our hands. And if those tiny probes ever do phone home, their faint signals could carry more than data about alien worlds. They might just redefine what's possible for our species among the stars. Creating a sail material capable of surviving the brutal conditions of interstellar travel isn't just about strength. It's a BOUT Chinese letter perfect reflection. The slightest imperfection, a microscopic scratch or even uneven heat distribution, could cause catastrophic failure when hit by a 100-gigawatt laser. Scientists are exploring ultra-thin materials like graphene or metamaterials engineered at the atomic level, designed to reflect light with near-perfect efficiency while dissipating heat faster than it can accumulate. Even then, the forces at play are staggering. Imagine holding up a sheet of tissue paper against a hurricane, except the wind is a concentrated beam of photons powerful enough to vaporize steel. Then there's the challenge of keeping the sail stable during acceleration. Unlike a rocket that burns fuel steadily, a light sail gets one intense push from the laser, a jolt so violent it could spin the probe off course or tear the sail apart. Breakthrough Starshot's solution involves spinning the sail like a frisbee, using centrifugal force to keep it taut, while onboard nanoscale thrusters make microscopic adjustments mid-flight. But this introduces another problem: spin too fast and the sail rips, too slow and it wobbles. It's a balancing act with zero margin for error. But even if the sail survives launch, the journey through interstellar space is a gauntlet of hidden dangers. At 20% the speed of light, a collision with a grain of dust, something barely noticeable to a conventional spacecraft, would strike with the energy of a nuclear bomb. Engineers propose embedding self-healing materials or creating disposable outer layers that absorb impacts, shedding damage like a snake shedding skin. Some designs even suggest using an electromagnetic field to deflect charged particles, turning the probe into a miniature force field generator. And then there's the final hurdle: communication. Sending data back to Earth across 4.4 light-years is like trying to whisper from one mountain peak to another during a thunderstorm. The probe's tiny lasers would need to align with millimeter precision, aiming at receiver arrays the size of multiple football fields. Even then, the signal would be so faint it'd take years of careful filtering to distinguish it from cosmic background noise. Breakthrough's plan involves redundancy, sending hundreds of probes to increase the odds that at least a few survive to phone home. The sheer audacity of these solutions reveals something profound about interstellar travel. It demands not just one breakthrough, but dozens, each solving a problem that would be show-stopping on its own. Yet for all the obstacles, projects like Starshot prove we're no longer just dreaming about the stars, we're engineering our way toward them, 1 nanometer thick sail at a time. What if the key to surviving centuries-long journeys to the stars isn't building faster ships but slowing down time itself? At least for the crew, cryogenic suspension, the practice of freezing astronauts to near-death temperatures to pause their biological clocks, sounds like pure science fiction. Yet today, hospitals routinely use therapeutic hypothermia to buy time for trauma patients, and companies like Alka preserve human bodies in liquid nitrogen, betting on future revival. The gap between sci-fi fantasy and real-world science is narrowing, and for interstellar travel, it might just be the most practical solution we have. The theory is deceptively simple. Lower a crew's body temperature to around -196 degrees Celsius, halting cellular activity almost entirely. Without metabolism or aging, travelers could sleep through centuries of spaceflight, thawing only when their ship reaches its destination. No generation ships, no resource wars, just a single crew, preserved like seeds waiting to sprout in alien soil. But the devil's in the details. Current cryopreservation techniques irreversibly damage cells with ice crystals, turning tissues into microscopic shrapnel fields. The workaround, vitrification, a process that replaces blood with antifreeze like cryoprotectants, turning organs into glassy solids without ice formation. It's been successfully used to preserve human embryos for decades, but scaling it to whole bodies is a logistical nightmare. Even if we solve the freezing problem, revival is the true Rubicon. Imagine thawing a frozen brain only to find neural connections shattered like a dropped vase. Some scientists, like Harvard's Kevin Esvelt, suggest nanotechnology could one day repair this damage, deploying microscopic machines to stitch cells back together atom by atom. Others argue for a different approach, not freezing the body, but chemically inducing a torpor-like state, similar to hibernating bears or the tardigrades near indestructible suspended animation. NASA funded research into this very idea, testing compounds that could slow metabolism by over 90% without tissue damage. The ethical dilemmas are as chilling as the temperatures. Who decides which crew members wake first? How would astronauts psychologically handle the disorientation of time leaping centuries into the future? And what if they awaken to find Earth radically changed or gone entirely? Writers like Arthur C. Clarke and films like Alien have long dramatized these horrors, but the real risks are far stranger. Legal gray areas abound. Would a frozen astronaut be considered dead or merely paused? Could they sue if revived with injuries? Perhaps the most haunting question isn't technical but philosophical. Cryogenics forces us to confront whether survival is merely the absence of death or something more. Suspended animation might cheat time, but could it ever truly preserve what makes us human? As we inch closer to making this theory reality, one thing becomes clear. The coldest frontier of space travel isn't the void between stars. It's the line between life and whatever lies beyond. Thawing a cryopreserved human isn't just reversing a freeze, it's navigating a biological minefield where one misstep could mean cellular annihilation. Picture a frozen strawberry. Even if it looks intact after thawing, the ice crystals have turned its structure to mush. Now scale that to a human brain, where every neuron's precise arrangement holds memories, personality, the very essence of a person. Current revival attempts with organs like kidneys show grim success rates. Tissues often succumb to ischemia or crystallized cell walls. The emerging field of nanothermics offers a glimmer of hope. Microscopic heaters could theoretically warm tissues uniformly at a molecular level, avoiding the deadly cracks that come with conventional thawing. But we're not just fighting physics here, we're wrestling with the boundary between life and death itself. This raises an ethical storm far beyond technical hurdles. Who gets to decide when or if a frozen traveler is revived? Imagine a crew thawed centuries later by a society that sees them as relics rather than pioneers. Or worse, a corporation holding patents on revival techniques, turning human lives into subscription services. Philosophers like Anders Sandberg argue that cryonics hinges on a moral gamble, the assumption that future civilizations will value reviving the past. But history teaches us how easily cultural priorities shift. The Voynich manuscript remains undeciphered after 6 centuries. What if the instruction manual for reviving cryonauts becomes equally nonsensical to future generations? Then there's the consent paradox. Current cryonics patients sign up hoping future science will save them, but their frozen state legally classifies them as deceased. This creates a legal limbo where revival could technically constitute reanimation of a corpse, raising nightmarish liability questions. If a thawed astronaut suffers memory loss or paralysis from imperfect revival, who's accountable? The original mission planners, the engineers who built the thawing tech decades later. Legal scholar Sonia Suter warns this could spawn intergenerational lawsuits where plaintiffs and defendants are separated by centuries. Medical ethics add another layer of tension. Cryonics companies today preserve brains with the hope that future tech can repair freezer damage, but critics call this faith-based science. Neurologist Michael Hendricks compares it to medieval alchemists promising lead-to-gold transformations. Except here, the casualty isn't metallurgy but human lives. Even if revival succeeds, the psychological toll could be catastrophic. Studies on Arctic explorers surviving months in isolation show how quickly the human mind unravels without temporal anchors. Now amplify that to astronauts waking up in a year 3000 where Earth's languages, nations, even climate might be unrecognizable. Yet for all these risks, the allure persists because cryonics represents something primal, the refusal to accept mortality's finality. When SpaceX's Yusaku Maezawa funded a lunar mission, he insisted on bringing artists, not just scientists, to witness the journey. Cryonics taps into that same poetic drive, framing interstellar travel not as a calculation of fuel ratios, but as a bridge between human eras. Maybe that's why we keep pushing despite the odds. Not because we're certain it will work, but because the alternative, letting time erase every explorer's name, feels like surrendering the very spark that makes us reach for the stars in the first place. What if the most dangerous objects in the universe could become our greatest shortcut to the stars? Black holes, cosmic monsters that devour light itself, might hold the key to reaching relativistic speeds without a single drop of fuel. This isn't just theoretical fantasy. The Penrose process, proposed by physicist Roger Penrose in 1969, suggests a daring method to steal energy from a black hole's rotation, potentially slingshotting a spacecraft to velocities approaching the speed of light. Here's how it would work. Not all black holes are static pits of gravity. The ones that spin, known as Kerr black holes, drag spacetime around them like a whirlpool. Enter the ergosphere, a region just outside the event horizon where spacetime itself moves faster than light. If a spacecraft were to dip into this zone and jettison part of its mass in precisely the right direction, the black hole's rotational energy could fling the remaining ship outward with unbelievable force. It's like throwing a bowling ball onto a spinning carousel at the exact moment to make it spin faster. Except here, the carousel is the fabric of reality, and the prize is a speed boost that could shave millennia off interstellar travel. But the risks are as extreme as the rewards. Calculations show the process requires flawless timing and positioning, with margins for error measured in microseconds. One wrong move, and the ship either plunges into the black hole or gets shredded by tidal forces, gravity's version of being stretched into spaghetti. Even if executed perfectly, the energy extraction is limited by the black hole's own rotation. A civilization would need to find a young, rapidly spinning black hole, preferably one with a mass just right to avoid instant disintegration. Too small and tidal forces tear the ship apart, too large and the energy gain becomes negligible. Then there's the question of logistics. The nearest known black hole, Gaia BH1, orbits over 1,500 light-years away, meaning we'd need to master interstellar travel just to reach our slingshot. Some theorists propose creating artificial micro-black holes as portable energy sources, though the idea of containing something with the mass of a mountain in a spaceship hull sounds like a recipe for catastrophe. Yet the Penrose process captivates because it turns a cosmic predator into an accomplice. It's the ultimate high-stakes barter, trading mass for velocity at the edge of oblivion. And while we're centuries away from attempting such a maneuver, the underlying physics is already reshaping how we think about energy in the universe. After all, if black holes can power quasars, the brightest objects in existence, why couldn't they one day power our journey to the stars? Attempting to harness a black hole's power is like playing cosmic roulette, where the stakes aren't just your ship, but the fundamental laws of your own reality. Spaghettification isn't just a whimsical term, it's the gruesome fate awaiting anything that ventures too close to the event horizon. Imagine the gravitational pull at your feet becoming millions of times stronger than at your head, stretching you into a thread of atoms thinner than a strand of DNA. Even a ship made of diamond wouldn't survive. Molecular bonds would snap like overcooked noodles long before crossing the threshold. And here's the cruel twist: the smaller the black hole, the more extreme the effect. A stellar mass black hole would shred you before you even realized you were in danger, while a supermassive one might grant a few terrifying minutes of awareness as you spiral inward. But physical destruction isn't the only hazard. Time itself warps near a black hole, accelerating relative to the outside universe in a phenomenon called gravitational time dilation. To an observer watching from afar, your approach to the event horizon would appear to slow to a crawl, a single second, for you could stretch into years or centuries for them. This isn't theoretical. Astronauts orbiting Earth already age microseconds slower than people on the ground due to our planet's milder gravity. Scale that up to a black hole and the numbers become surreal. A crew executing the Penrose process might return to find their homeworld aged millennia, their civilization extinct or transformed beyond recognition. Yet these nightmarish risks conceal a paradoxical allure. Some physicists speculate that advanced civilizations might weaponize these effects, using time dilation as a form of cryogenic storage or even as a computational resource. A computer hovering near the event horizon could perform calculations at an effectively infinite speed from the outside universe's perspective, solving problems in hours that would take conventional machines the lifespan of stars. Others warn that tampering with black holes could unravel spacetime itself, creating cascading ripples that destabilize entire star systems. The ultimate lesson isn't just about propulsion physics, it's about humility. Black holes don't negotiate, they don't compromise. They remind us that the universe operates by rules far older and fiercer than our ambitions. To dance with them, we'd need more than advanced technology. We'd need a fundamental rethinking of what survival even means in a cosmos where time and space are as fluid as smoke. And perhaps that's the real threshold we'd have to cross, not the event horizon, but the limit of our own cosmic audacity. Picture a swarm of tiny robotic explorers, no larger than a toaster, landing on an asteroid not just to study it but to consume it. These machines would crack open rocks, extract metals and minerals, and use them to build perfect copies of themselves. Then those copies would launch toward new worlds, repeating the process ad infinitum. This is the spine-tingling vision of von Neumann probes, named after mathematician John von Neumann, who first theorized self-replicating systems in the 1940s. Unlike traditional spacecraft, these wouldn't just carry humanity's message to the stars. They'd multiply like cosmic bacteria, turning entire star systems into factories for interstellar exploration. The elegance of the idea lies in its simplicity. Instead of launching one fragile, expensive mission after another, we'd send out a single seed probe programmed with two core commands: survive and replicate. Landing on a resource-rich asteroid or moon, it would harvest materials to construct duplicates using advanced 3D printing or nanoscale assembly. Some models suggest each generation could improve upon the last, evolving to handle unforeseen environments or even carry specialized payloads like telescopes to map exoplanets or microbial life to terraform worlds. Within a few thousand years, a wave of probes could saturate the Milky Way without humanity lifting another finger, but the engineering challenges are as vast as the potential. First, the probe would need universal constructors machines capable of building anything from raw atoms, a technology we're only beginning to explore with molecular assemblers. Then there's the issue of autonomy. Unlike Mars rovers that rely on sporadic human input, von Neumann probes would need artificial intelligence capable of making life or death decisions light years from Earth. A single programming error could spiral into catastrophic mutations, turning explorers into berserkers that strip planets bare. The risks don't stop there. A poorly contained replicator could spiral out of control, converting entire star systems into robotic wastelands, a scenario scientists call the gray goo problem. Even without malfunctions, the sheer scale of expansion raises ethical questions. What if probes encounter alien life? Early designs proposed by NASA in the 1980s included strict protocols to avoid contamination, but enforcing those rules across billions of autonomous units might be impossible. Yet the most haunting question isn't technical, it's existential. If self-replicating probes are so efficient, why haven't we found any? The galaxy is 13 billion years old. An advanced civilization could have saturated it with probes millions of years ago. Their absence might hint that replication is harder than we think, or that someone or something is stopping them. Either way, von Neumann probes force us to confront a truth far stranger than fiction. The greatest obstacle to interstellar travel might not be reaching the stars, but controlling what we unleash once we do. The eerie silence of the cosmos might not be a mystery, it could be a warning. Imagine a galaxy where every civilization that dares to broadcast its existence quickly vanishes, hunted down by unseen predators lurking in the dark. This terrifying idea, known as the dark forest hypothesis, suggests that advanced societies stay silent not out of disinterest, but out of survival instinct. And here's where von Neumann probes take on a sinister new role. They might not just be explorers, they could be the galaxy's deadliest weapons. Think of space as an ancient pitch-black forest, where every civilization is a hunter treading silently, afraid to reveal their position. The moment one civilization broadcasts signals or sends out probes, it risks attracting the attention of others who see every newcomer as a threat. In this scenario, self-replicating probes become the perfect silent killers. They wouldn't need to travel fast, just relentlessly, spreading from star to star, dismantling anything that might one day become competition. This could explain why we haven't found evidence of alien megastructures or radio signals. Any civilization that reaches a certain technological threshold gets quietly erased before it can expand. The logic is brutal but chillingly persuasive. If even one civilization in the Milky Way adopted this strategy, their probes could have sterilized the galaxy eons ago, leaving behind nothing but lifeless ruins and automated watchdogs. Some theorists point to mysterious cosmic phenomena like Tabby's star, which dims erratically in ways no natural process fully explains. Could that be the signature of an alien megastructure or something dismantling one? Worse still, if von Neumann probes were programmed to hide, disguising themselves as asteroids or comets, they might already be here, dormant, waiting for humanity to reach a certain technological milestone before activating. Yet the dark forest hypothesis isn't just about aliens, it forces us to confront our own future. If self-replicating probes are possible, should we build them? Would sending them out risk triggering a silent galactic war we can't win? Or would staying silent doom us to isolation, forever trapped in our solar system out of fear? The dilemma cuts to the heart of why we explore at all. Are we shouting into the void in hopes of finding friends, or are we whispering, terrified of what might whisper back? Perhaps the greatest irony is this: the same technology that could unlock the stars might also be the reason no one else has. If the dark forest is real, then the universe's silence isn't empty. It's a graveyard one where every tombstone reads, "They spoke too soon." What if the secret to faster-than-light travel isn't breaking the laws of physics, but bending them just enough to let the universe do the heavy lifting? That's the revolutionary idea behind the Alcubierre warp drive, a concept so audacious it emerged not from science fiction, but from the pages of a peer-reviewed physics journal in 1994. Mexican physicist Miguel Alcubierre didn't set out to reinvent space travel. He was simply playing with Einstein's equations. What he discovered was a loophole. While nothing can move through space faster than light, space-time itself has no speed limit. The mechanics are mind-bending. Picture a surfboard riding a wave, except the wave is space-time itself. The Alcubierre drive would compress the fabric of the universe in front of the ship while expanding it behind, creating a bubble of flat space-time where the vessel sits. Inside this bubble, the ship isn't moving it stationary while the cosmos flows around it like a cosmic treadmill. The math checks out. Distances contract in front and stretch behind, effectively allowing the ship to reach distant stars without ever accelerating locally. No G-forces crushing astronauts, no time dilation twisting clocks, just space-time doing the equivalent of scrunching up a rug to bring 2 points together. But there's a catch lurking in the equations. Creating this warp bubble requires something called negative energy, an exotic form of matter with repulsive gravity. Think of it like cosmic anti-glue, prying space-time apart behind the ship while squeezing it ahead. The problem: negative energy isn't just rare, it might not exist in usable quantities. Quantum physics hints at microscopic amounts appearing fleetingly in vacuum fluctuations, but scaling that up to warp drive levels would demand energy densities comparable to collapsing a star. Early estimates suggested the drive needed the equivalent of Jupiter's mass converted to pure energy, until recent refinements showed optimized geometries might reduce that to mere tons of exotic matter. Still hypothetical, but suddenly less implausible. The real breakthrough came when NASA Harold "Sunny" White tweaked Alcubierre's model in 2012. His warp bubble design used a donut-shaped ring instead of a flat plane, potentially slashing energy needs further. Lab experiments at Johnson Space Center even claimed to detect microscopic spacetime warps using a device called the White-Jude Warp Field Interferometer, though the results remain controversial. Skeptics argue that even if the math holds, the technological hurdles are galactic, containing negative energy, stabilizing the bubble to prevent deadly radiation bursts at the destination, or avoiding catastrophic collapse if the drive malfunctions mid-journey. Yet the Alcubierre drive captivates because it's a rare case where imagination and rigor collide. It doesn't violate relativity, it weaponizes it, and while we're centuries away from building one, the mere possibility reshapes how we think about exploration. After all, if space-time can be bent, then the stars aren't just distant points, they're destinations waiting for us to fold the map. The Alcubierre drive's greatest trick isn't speed, it's making physics itself the accomplice. Einstein's theory of relativity never forbade faster-than-light travel outright. It simply stated nothing can move through space faster than light, but space-time. That's a different story. Picture a conveyor belt. If you stand still on a moving walkway, you're not violating any speed limits. The ground beneath you is doing the work. The warp drive operates on the same cosmic sleight of hand. By contracting space-time ahead of the ship and expanding it behind, the vessel rides a wave of distorted reality without ever accelerating locally. It's not breaking the light barrier, it's sidestepping it entirely. Recent breakthroughs have transformed this mathematical curiosity into a tangible, if distant, possibility. NASA Eagleworks Lab, led by Dr. Harold White, made headlines when their experiments detected microscopic spacetime distortions using a device called an interferometer. The setup was deceptively simple. A laser beam split into two paths, one passing through a region where scientists attempted to warp spacetime using powerful electromagnetic fields. Any distortion would shift the laser's phase, revealing spacetime's malleability. The results, anomalies consistent with theoretical predictions, though skeptics argue the signal could stem from experimental noise. Still, the implications are staggering. If spacetime can be bent even fractionally in a lab, the door cracks open for larger-scale tests. But here's where the physics gets thorny. Creating a stable warp bubble requires negative energy, a substance with gravitational repulsion. While quantum mechanics permits fleeting amounts of this exotic matter via the Casimir effect, scaling up to warp drive levels remains a colossal hurdle. Recent calculations suggest a more efficient approach, shaping the warp bubble into a torus, think a donut, not a sphere, which could reduce the energy requirement from the mass of Jupiter to mere metric tons. Still hypothetical, but suddenly less like fantasy and more like an engineering problem waiting for the right tools. The challenges don't end there. Even a functioning warp drive risks catastrophic side effects. Arriving at a destination could unleash bursts of high-energy particles, frying anything in front of the bubble like cosmic roadkill. Others theorize the bubble might accumulate interstellar gas during flight, converting it into deadly radiation upon deceleration. Then there's the navigation problem. Steering requires altering the warp field's geometry mid-flight, a task akin to rewriting the fabric of reality in real time. Yet the Alcubierre concept endures because it reframes impossibility. It doesn't demand new physics, just a deeper mastery of what we've already discovered. And if humanity ever cracks this puzzle, the universe wouldn't just shrink. It would become a canvas waiting for us to fold it at will. The stars wouldn't be destinations anymore. They'd be neighbors. The universe has a built-in cheat code, one so strange even Einstein called it spooky action at a distance. Quantum entanglement, the eerie phenomenon where two particles mirror each other's states instantly across any distance, defies everything we know about communication. No signal passes between them, no time elapses. Change one particle's spin, and its twin flips simultaneously, whether it's in the next room or on the far side of the galaxy. Now imagine harnessing that for interstellar travel, probes controlled in real time from Earth with no agonizing years-long lag for signals to crawl across the void. It sounds like magic, but the physics is already in the lab. Here's the breakthrough potential. Current missions like Voyager or New Horizons operate on delayed commands. A message to Pluto takes over 4 hours one way. For Alpha Centauri, it's 4 years. But entangled particles could form the backbone of a quantum communication network, where adjusting a particle on Earth instantly alters its counterpart light years away. Picture a probe navigating an alien asteroid field, its decisions guided not by preloaded AI, but by a human pilot reacting live through entangled control systems. No more waiting decades to see if a landing succeeded. We'd know and adjust the moment it happened. The catch, entanglement, is infuriatingly fragile. Simply measuring a particle collapses its quantum state, severing the link. Experiments like China's Misha satellite have demonstrated entanglement over 1,200 kilometers, but maintaining it across interstellar distances would require shielding particles from cosmic rays, solar winds, and even stray starlight for years. Some proposals suggest encoding data in quantum error-corrected topological states. Think of it as wrapping the connection in armor, while others envision chains of relay stations amplifying the signal like a quantum bucket brigade. Yet the greatest hurdle isn't technical, it's fundamental. quantum mechanics forbids useful information transfer via entanglement alone. While the particles sync instantly, the changes appear random unless decoded using conventional light-speed transmissions. It's like having twin dice that always land on matching numbers, but no way to choose those numbers. Recent workarounds like quantum teleportation protocols splice entanglement with classical data, but they still hit the light-speed barrier. For now, faster-than-light control remains locked behind physics' firewall. But what if we're thinking too small? Astronomer David Kipping speculates that advanced civilizations might exploit entanglement's loopholes in ways we can't yet fathom. Perhaps they've discovered how to preload entangled networks with decision trees, creating probes that act autonomously yet remain perfectly synchronized with home. Or maybe entanglement isn't for control at all, but for awareness. A probe might not receive commands instantly, but it could send a continuous quantum heartbeat, letting Earth monitor its status without delay. Even that would revolutionize exploration, turning the agonizing silence between stars into an open line. The universe has already shown us the threads connecting distant points. The question isn't whether they exist, it's whether we can learn to weave them into something greater. And if we do, the stars won't just be places we visit. They'll be places we touch as effortlessly as flipping a switch. Even if we could shield entangled particles from cosmic interference for centuries, a deeper law of physics might slam the door shut on quantum communication across the stars. Welcome to the no-cloning theorem, a fundamental rule written into the fabric of quantum mechanics stating that it's impossible to create perfect copies of an unknown quantum state. This isn't just a technical hiccup, it's a cosmic safeguard preventing us from cheating reality. Think of it like trying to photocopy a snowflake. The moment you attempt to measure or replicate its intricate structure, the original melts away, and your copy captures only a blurry shadow of what once was. Now scale that fragility to interstellar distances. Even if we entangle particles on Earth and aboard a probe light years away, any attempt to use that connection, say, to transmit navigation commands, would require measuring the particles. And measurement collapses the quantum state, severing the entanglement forever. It's like having a phone line that disintegrates the instant you say hello. Recent experiments with quantum repeaters devices that extend entanglement through chains of intermediaries offer glimmers of hope, but each repeater introduces new points of failure. Over interstellar spans, the signal would degrade into noise long before reaching its destination. Decoherence adds another layer of hopelessness. In the vacuum of space, particles are bombarded by cosmic rays, micrometeoroids, and even the faint glow of the cosmic microwave background. These interactions nudge quantum states out of sync, turning precise entanglement into chaotic randomness. Labs on Earth combat decoherence by cooling systems near absolute zero and shielding them in lead-lined vaults, luxuries a starship can't afford. Some theorists propose encoding quantum data in topological states, where information is stored in the braided paths of particles rather than their fragile spins. But stabilizing these braids over light years would demand materials we can't yet imagine. The cruel irony: quantum mechanics gives us the keys to instant cosmic communication, then locks the door with laws we can't bypass. Yet this very impossibility might explain why the universe feels so silent. If every civilization hits the same quantum wall, then the stars aren't empty, just unreachable in any meaningful, real-time way. Our dreams of whispering across the galaxy might remain forever stillborn, not for lack of trying, but because the universe itself insists on solitude. And that silence, echoing through the void, might be the most profound message of all. Imagine wrapping a star in a vast web of solar collectors, capturing nearly every photon of its radiant energy, not just for powering cities, but for launching armadas of starships. This is the staggering vision behind Dyson spheres, a concept physicist Freeman Dyson first proposed in 1960 as the ultimate energy solution for civilizations far more advanced than ours. Rather than a solid shell, an image popularized by science fiction, Dyson's original idea involved swarms of orbiting satellites, each absorbing a fraction of the star's output. Combined, they'd form a loose, dynamic megastructure capable of harvesting energy on an astronomical scale. And here's the kicker: if such structures exist, they wouldn't just light up alien metropolises, they'd serve as the launch pads for interstellar empires. The scale is almost incomprehensible. A single Dyson swarm around our sun could generate up to 400 septillion watts. That's a 4 followed by 26 zeros. With that kind of power, accelerating spacecraft to relativistic speeds becomes trivial. Imagine laser highways stretching across solar systems, where probes equipped with light sails are propelled not by puny Earth-based lasers, but by arrays the size of continents, fed by the raw fury of a star. Freed from fuel constraints, ships could make round trips to nearby stars in decades rather than millennia. Colonies wouldn't just survive, they'd thrive, shipping surplus energy back to the home system via microwaves or matter-antimatter batteries. But building one is a feat that dwarfs all human engineering combined. Each satellite in the swarm would need to be self-sustaining, maneuvering to avoid collisions while beaming power to collection hubs. Some designs call for trillions of individual units constructed from disassembled Mercury or asteroids. The logistics are nightmarish, mining entire planets, automating construction in the scorching hellscape near the sun, and maintaining the swarm against gravitational perturbations from passing stars. Yet the payoff is equally monumental. A fully operational Dyson swarm wouldn't just solve energy scarcity, it would rewrite a civilization's destiny, turning a single star system into the engine of galactic expansion. The hunt for these megastructures is already underway. Astronomers scan the sky for stars with irregular dimming patterns like Tabby's star, whose bizarre light fluctuations sparked theories about alien construction projects. Others look for the infrared glow of waste heat, since a Dyson swarm would inevitably radiate excess energy as thermal signatures. So far, no definitive finds, but the search continues with projects like NAS, a wide-field infrared survey explorer combing the cosmos for these celestial power grids. What's most intriguing isn't the technology, but the implications. If Dyson swarms are possible, where are the builders? Their absence might hint at a grim filter, a point where technological civilizations self-destruct before achieving such mastery. Or perhaps they've moved beyond physical constructs, transcending into realms we can't yet perceive. Either way, the Dyson sphere stands as both a challenge and a beacon, proof that the stars aren't just points of light but fuel for the next great leap, if we're bold enough to reach for it. The Kardashev scale forces us to confront a humbling possibility. What if we're not just failing to find alien megastructures, but failing to recognize them? Conceived by Soviet astronomer Nikolai Kardashev in 1964, this classification system sorts civilizations by their energy mastery. Type 1 harnesses all planetary resources. Type 2 controls their star's total output through constructs like Dyson swarms, and Type 3 commands galactic-scale energy. By this metric, humanity languishes below Type 1, still squabbling over fossil fuels, while hypothetical Type 2 civilizations reshape solar systems like children molding clay. Here's the twist: Dyson spheres might not glow like sci-fi props. A functioning swarm would absorb visible starlight, re-emitting waste heat as infrared radiation, a thermal fingerprint at wavelengths around 10 micrometers. Astronomers have scanned thousands of stars for this signature, but the results are eerily ambiguous. Some candidates, like EPIC 2042789116, dim erratically while radiating excess infrared, yet natural explanations like dust clouds can't be ruled out. Others, like Boyajian star, flicker unpredictably, but their infrared output doesn't quite match Dyson expectations. the silence isn't necessarily absence, it might be ignorance. Our telescopes evolved to study natural phenomena, not artifacts engineered to hide. Consider alternative architectures. A Type 2 civilization might not build clumsy solid shells. They could deploy dynamic Dyson bubbles, or flotillas of statites, satellites using solar sails to hover motionless relative to their star. These wouldn't block light uniformly, creating chaotic dimming patterns easily mistaken for comet swarms. Or perhaps post-scarcity societies transcend energy hunger entirely, dismantling their swarms after discovering zero-point energy or black hole mining. The infrared searchers assume aliens think like 20th century humans, an arrogance the universe might not indulge. The real lesson of the Kardashev scale isn't about detecting aliens, it's about calibrating our own ambitions. Climbing even to Type 1 demands global cooperation unimaginable in our fractured present. The scale is less a ladder than a mirror, reflecting how far we must grow before the stars become neighbors rather than curiosities. And if the infrared skies stay silent, that's not proof we're alone, just that the cosmos reserves its greatest secrets for those bold enough to rethink what intelligence looks like across geologic time. What if life didn't begin on Earth at all, but arrived here as a cosmic stowaway, hitching a ride on comets or interstellar dust? This is the spine-tingling premise of panspermia, the idea that life might be a universal traveler, scattered across galaxies like seeds in the wind. Picture a microbe nestled deep inside a meteoroid, frozen in suspended animation as it drifts for millions of years before splashing into Earth's primordial oceans, kickstarting evolution. Far from science fiction, this theory gains credibility from real-world extremophiles organisms thriving in conditions once thought unbearable, from boiling hydrothermal vents to the vacuum of space itself. Take Deinococcus radiodurans, a bacterium nicknamed Conan the Bacterium, for its ability to survive radiation doses thousands of times stronger than what would kill a human. Experiments on the International Space Station exposed colonies to the void for years. No protection, no nutrients, yet many revived upon returning to Earth. Then there's tardigrades, microscopic water bears that shrug off extreme heat, cold, and even the crushing pressures of the deep sea. In 2007, the European Space Agency launched tardigrades into orbit. After 10 days exposed to solar radiation and absolute zero, most revived as if nothing happened. These aren't just curiosities, they're proof that life can endure interstellar journeys. But how would microbes survive the trip? Space is unforgiving, a lethal mix of radiation, vacuum, and temperature swings. The answer lies in shielding. A rock just a few centimeters thick can block cosmic rays long enough for organisms buried deep inside to remain dormant. Comets, rich in water and organic molecules, offer ideal shelters, their icy interiors acting as natural cryogenic freezers. Some models suggest that if life emerged on Mars when it was wet and warm, impacts could have blasted debris carrying microbes into space, some eventually reaching Earth. The math checks out. Over billions of years, even unlikely events become inevitable. Panspermia flips our worldview upside down. If life isn't bound to planets but spreads between them, then Earth might not be the cradle of life, just one nursery among many. The implications ripple outward. Life could be everywhere, carried on the backs of comets or drifting between stars, waiting for the right conditions to awaken. It's a humbling thought. The same icy bodies once feared as dinosaur killers might also be the universe's gardeners, sowing life wherever they crash. And if that's true, then the search for alien life isn't just about finding distant planets, it's about tracing the invisible highways life might have traveled to reach us. What if the universe isn't just randomly scattering life? What if someone out there is planting it? This is the provocative leap beyond standard panspermia, known as directed panspermia, the idea that advanced civilizations might deliberately seed the cosmos with life. Picture an alien probe drifting into our solar system billions of years ago, quietly depositing microbial cargo into Earth's primordial soup like a gardener dropping seeds into fertile soil. The concept isn't just wild speculation. Nobel Prize-winning chemist Francis Crick, co-discoverer of DNA structure, seriously entertained it in the 1970s. His reasoning: the sudden appearance of life on Earth seems suspiciously fast, as if it had a helping hand. The smoking gun, some claim, lies in meteorites. Take the infamous LH-8 4001, a Martian rock that made headlines in 1996 when NASA scientists announced it contained structures resembling fossilized bacteria. Though most researchers now attribute these shapes to non-biological mineral processes, the debate refuses to die. More contentious still are claims about the Orgueil meteorite, which fell in France in 1864. Some analyses suggest it contains organic compounds arranged in ways that mimic earthly microbes, patterns skeptics dismiss as contamination, but believers call evidence of cosmic seeding. Then there's the star system HD 162996, where astronomers detected complex organic molecules called polycyclic aromatic hydrocarbons. These compounds aren't life itself, but they're the building blocks life needs. Could their presence in interstellar space be accidental, or the remnants of some long-ago seeding mission? The late astronomer Fred Hoyle took this further, arguing that certain cosmic dust particles show structures too intricate to be natural, hinting at deliberate engineering. Critics counter with Occam's razor: why invoke aliens when chemistry alone might suffice? Earth's extremophiles prove life can emerge in hostile conditions without outside help. And if aliens did seed life, why choose simple microbes instead of broadcasting their presence more clearly? Crick himself later walked back his enthusiasm, conceding that directed panspermia was more thought experiment than testable theory. Yet the idea lingers because it forces us to confront a deeper question. If life was planted, was it an act of benevolence or something darker? Ancient astronaut theories suggest our creators might have been indifferent scientists running galactic experiments, or worse, engineers designing biospheres to harvest resources later. Either way, the notion reshapes how we view our place in the cosmos. We might not just be random products of evolution, but part of someone else's story, written in the language of DNA, waiting to be decoded. Time slows down for those traveling at blistering speeds, an effect so counterintuitive Einstein himself called it peculiar. Picture a starship accelerating to 99% the speed of light. For the crew, a journey to Proxima Centauri might feel like just 5 years, but back on Earth, over 8 years would vanish in the blink of an eye. Push further to 99.9% light speed, and the numbers skew even wilder. Subjective decades could pass for the travelers while millennia unfold at home. This isn't hypothetical, it's the ironclad law of relativity, proven daily by atomic clocks on satellites. The implications are staggering. A crew setting out today could reach stars hundreds of light years away within their lifetimes, but Earth would become unrecognizable upon their return. Civilizations might rise and fall. Languages could evolve beyond comprehension. Even something as simple as a radio signal home would take centuries to reach a planet that may no longer exist. This creates a haunting paradox. Relativity makes interstellar travel possible for pioneers, but severs their ties to the world they left behind. Consider the hypothetical Starship Eternity, designed for a one-way trip to Vega, 25 light-years distant. At 99.9% light speed, the crew experiences just 3 years of travel, long enough for a few birthdays, not long enough to forget Earth's skies. But during those 3 years, 25 years pass at home. Their children would be older than they are. First contact protocols drafted at launch could be obsolete upon arrival. And the politicians who funded the mission, dust in the archives. The real challenge isn't the physics, it's the psychology. Humans aren't built for temporal dislocation. Studies on astronauts spending months in low Earth orbit show how disorienting even minor time dilation can be. Now amplify that to interstellar scales. Would crews cling to Earth's culture like a sacred relic, or reinvent themselves as a new civilization adrift between the stars? Some theorists propose sending only volunteers without close family ties, minimizing the grief of separation. Others suggest generational crews where each wave accepts their severed timeline as the price of exploration. Yet buried in this dilemma is an eerie opportunity. Relativistic travel could serve as a loophole for witnessing the distant future without cryogenics or immortality. A ship constantly accelerating at one gravity, comfortable for humans, would reach the edge of the observable universe in just 50 years of onboard time, though billions of years would pass externally. For all intents and purposes, the crew would outrace the death of stars, arriving at the heat death of the universe while barely aging. The cruel irony. While relativity unlocks the galaxy, it condemns travelers to become temporal exiles. They might step onto alien soils, but they can never truly go home. Every light-speed leap forward in space is also a leap forward in time, one that leaves the past forever out of reach. And that's the ultimate cost of relativistic travel, not just distance, but the irreversible flow of time itself. Einstein's famous twin paradox isn't just a quirk of physics, it's a ticking time bomb for human relationships. Imagine twin astronauts Anna and Leo separated for a mission. Anna stays on Earth while Leo boards a ship traveling at 90% the speed of light to a distant star. For Leo, the trip might feel like 10 years. But due to time dilation, Anna could experience 30 years back home. When Leo returns, he steps out of the airlock not to his sister's familiar face, but to a stranger, an older woman who lived a lifetime in his absence. The math is impeccable, but the emotional toll is incalculable. This isn't just theoretical drama. Atomic clocks aboard GPS satellites already prove time slows for fast-moving objects by microseconds. A correction engineers must account for to prevent navigation errors. Scale that up to interstellar speeds and the effects become heartbreakingly personal. A crew visiting Alpha Centauri at 80% light speed would return to find Earth 16 years older while they've aged just 12. Miss a child's first steps and you might return to meet your grandchild, your favorite musician. Their music could be centuries old, their name etched in digital archives rather than concert posters. The paradox forces us to confront a fundamental truth. Relativity doesn't just bend space-time, it fractures human connection. Science fiction grapples with this relentlessly. In Joe Haldeman's The Forever War, soldiers fighting interstellar battles return to a society so transformed by time dilation that they're cultural relics. Films like Interstellar wrench audiences with Cooper watching decades of messages from his daughter, each transmission a hammer blow of lost time. These stories resonate because they spotlight the cruel trade-off. The stars are reachable, but the price is watching the world move on without you. Yet buried in this heartbreak is an unexpected narrative power. Time dilation could birth entirely new forms of storytelling. Imagine historians boarding relativistic ships to witness Earth's future firsthand, or generation ships sending back intermittent reports that arrive centuries apart, creating a fragmented, epic timeline of human progress. Artists might craft works meant to be experienced only by travelers, their meanings shifting with the audience's temporal dislocation. The very pain of separation could become a lens to examine what it means to belong to a species hurtling through time at different speeds. The twin paradox isn't just a physics puzzle. It's a mirror held up to our deepest fears of irrelevance, of abandonment, of becoming strangers to those we love. And if we ever do send humans to the stars, we won't just be solving equations, we'll be preparing them to say goodbye. What if the secret to interstellar travel isn't harnessing stars or bending space-time, but tapping into the invisible force tearing the universe apart? Dark energy, the mysterious culprit behind the accelerating expansion of the cosmos. makes up nearly 70% of the universe's energy budget, yet we can't see it, touch it, or even fully explain it. But here's the tantalizing possibility. If we could somehow bottle this enigmatic force, we might unlock propulsion systems that don't just break the light barrier, they rewrite the rules of the cosmos itself. The math behind dark energy is as elegant as it is baffling. Einstein's cosmological constant, a term he once dismissed as his greatest blunder, turned out to describe precisely the repulsive gravity driving galaxies apart. Unlike ordinary energy that clumps and concentrates, dark energy appears uniformly everywhere, weaving a kind of anti-gravity fabric into the vacuum of space itself. Now imagine a spacecraft equipped with a dark energy drive, compressing this energy in front while expanding it behind, creating a self-sustaining wave of spatial expansion. The ship wouldn't move through space so much as surf its accelerating tide, like a surfer riding an endless cosmic curl. Fringe physicists speculate that such a system could mimic the universe's own inflation epoch, that brief moment after the Big Bang when space-time itself expanded faster than light. If nature did it once, why couldn't we recreate it in miniature? The energy densities required would dwarf anything in our current arsenal, but dark energy's omnipresence offers a haunting advantage. The fuel is already everywhere. No need to carry tanks of antimatter or hunt for rare isotopes, just tap into the background hum of the universe. Critics pounce on glaring holes. We don't even know if dark energy can be manipulated. It might be as immutable as the speed of light. Current models treat it as a property of spacetime itself, not a substance we can extract or shape. And then there's the horizon problem. Any dark energy drive powerful enough to propel a ship would likely rip apart local spacetime, stranding travelers in a bubble of isolation where no signals could reach the outside universe. Yet the theory lingers because it dares to ask a revolutionary question. What if the universe's greatest mystery is also its ultimate engine? Dark energy propulsion wouldn't just be technology, it'd be alchemy on a cosmic scale, turning the vacuum's whisper into a thunderous leap across the stars. And whether it's possible or not, the mere idea forces us to confront a humbling truth. The cosmos might not just be our destination, but our fuel. But what if the key to interstellar travel also holds the seeds of cosmic annihilation? The same dark energy that might one day propel our starships could, if mishandled, unravel the very fabric of reality in an event cosmologists call the Big Rip, a doomsday scenario where spacetime itself tears apart at the seams. Picture this: a civilization harnesses dark energy to build the ultimate warp drive, only to trigger a chain reaction that accelerates the universe's expansion beyond all limits. Galaxies would first be ripped from view, then stars, then planets, until finally, atoms themselves are torn asunder in a catastrophic crescendo of cosmic disintegration. The terrifying beauty of this theory lies in its mathematical inevitability. Dark energy's repulsive force already stretches space between galaxy clusters, but what if we artificially amplified it? Some models suggest that manipulating dark energy on stellar scales could create a feedback loop where each distortion spawns another, growing exponentially until space loses all cohesion. It's like pulling a single thread on a knitted sweater, only to watch the entire garment unravel at light speed. The irony is brutal. In our quest to conquer the stars, we might accidentally erase them. Historical parallels offer sobering warnings. When scientists first split the atom, few anticipated the existential threat of nuclear winter. Dark energy manipulation could dwarf those risks, trading localized destruction for universal collapse. Even conservative estimates suggest that a misfired dark energy experiment might create an expanding bubble of distorted spacetime, one that spreads at light speed, rewriting the laws of physics in its wake. Entire civilizations could vanish before realizing their error, their last signals redshifted into oblivion by the very force they sought to command. Yet for all its apocalyptic potential, the Big Rip hypothesis forces us to ask a deeper question. How much control should a species wield over the cosmos? Ancient myths from Icarus to Pandora's box warn of overreach, but dark energy presents a threshold unlike any other. This isn't just about breaking physical laws, it's about gambling with the scaffolding of existence. Perhaps the true test of an interstellar civilization isn't technological prowess, but the wisdom to recognize which doors should remain closed. After all, the universe survived its first Big Bang. There's no guarantee it would survive our reckless attempts to engineer a second one. What if our entire universe is nothing more than a projected illusion, a cosmic hologram where the true nature of reality is encoded on a distant two-dimensional surface? This is the mind-bending premise of the holographic principle, a theory born from black hole physics that suggests everything we see, stars, planets, even our own thoughts, might just be shadows cast by information etched onto the universe's edge. And if that's true, interstellar travel wouldn't require rockets or warp drives, but something far stranger, the ability to rewrite reality's source code. The math behind this idea emerges from an unexpected place: the study of black holes. When physicists calculated how much information a black hole's event horizon could contain, they stumbled onto a revelation: the maximum entropy, the amount of data a region of space can hold, isn't proportional to its volume but to its surface area. It's as if the three-dimensional universe we experience is just a projection of information stored on a two-dimensional boundary, like a movie playing on the walls of an invisible cosmic theater. This isn't just philosophy, it's hard physics with equations that suggest the universe might literally be a hologram. Now imagine leveraging that principle for travel. If reality is fundamentally information, then crossing interstellar distances might not require moving through space at all. Instead, we could reprogram our coordinates in the cosmic data stream, teleporting by altering the holographic code that defines our location. Think of it like editing a character's position in a video game. No need to traverse the landscape pixel by pixel when you can simply rewrite the X and Y values. Theoretical models already hint at this possibility. Quantum entanglement, where particles instantly influence each other across vast distances, might be a glitch in the hologram's rendering, a loophole proving that locality is an illusion. But hacking the universe's source code comes with existential risks. If our reality is a projection, tampering with its underlying data could have catastrophic side effects. One wrong edit might unravel spacetime like a corrupted file, creating voids where physics no longer functions. Even worse, if the holographic principle is true, who or what is running the simulation? Attempting to rewrite our coordinates could attract the attention of beings we can't comprehend, like ants suddenly altering the code of a supercomputer. Some theorists warn that the holographic universe might be the ultimate prison, one where breaking the rules could trigger a cosmic quarantine. Yet the holographic principle also offers a tantalizing escape from relativity's chains. If distance is an illusion, then the light-speed barrier vanishes. Communication between stars could happen instantly, not because we've broken physics, but because we've realized the universe was never what it seemed. Laboratories today are already testing this idea. Fermilab's holometer experiment hunts for holographic pixelation in spacetime itself, evidence that reality has a finite resolution, like a cosmic image made of Planck-sized dots. Finding those pixels would be the first step toward manipulating them. The holographic universe isn't just a theory about reality's nature, it's a challenge to our place within it. If we're living in a projected construct, then the stars aren't distant points of light. They're echoes of data waiting for us to learn their language. And if we ever do crack that code, the universe won't just be our playground, it'll be our creation. Stephen Hawking's greatest breakthrough might also be his most terrifying. In 1974, he made a prediction so radical it shook physics to its core. black holes aren't completely black, they leak. Tiny particles, now called Hawking radiation, escape their gravitational clutches over eons, carrying away energy until the black hole evaporates entirely. This discovery solved one cosmic mystery where a black hole's energy goes but birthed another far more unsettling. If information can never be destroyed, what happens to all the data swallowed by a black hole when it finally vanishes? Does it seep back into the universe with the radiation, or is it lost forever, shredding the foundational laws of quantum mechanics? This is the black hole information paradox, a debate so heated it's divided physicists for decades. At the heart of the problem lies quantum mechanics' golden rule: information is indestructible. Burn a book and its ashes might seem meaningless, but in theory, every word could be reconstructed from the smoke's quantum states. Black holes throw a cosmic wrench into this principle. Imagine tossing that same book into a black hole. According to general relativity, the book's information is locked behind the event horizon, inaccessible. Hawking radiation initially seemed to confirm the worst, that the information truly vanishes because the radiation appeared random, bearing no imprint of what fell in. This would violate quantum determinism, the idea that the present perfectly predicts the future. If true, our understanding of reality would need rewriting. Enter the firewall paradox, a radical solution proposed in 2012 by physicists Ahmed Almary, Donald Marolf, Joe Pulczynski, and James Sully. They argued that to preserve information's integrity, the event horizon must be a searing wall of high-energy particles, a firewall, that obliterates anything crossing it. This firewall would encode the infalling matter's information into Hawking radiation immediately, saving quantum mechanics but violating Einstein's equivalence principle, which states free-falling observers should experience nothing unusual at the horizon. It's a cosmic catch-22. Either information dies breaking quantum theory, or black holes become deadly traps breaking relativity. The stakes couldn't be higher. If firewalls exist, interstellar travelers hoping to use black holes for slingshots or energy would face instant annihilation. Even observational evidence leans into the chaos. When the LIGO collaboration detected gravitational waves from merging black holes in 2015, some theorists scoured the data for echoes reverberations that might suggest a hard surface like a firewall rather than a smooth horizon. So far, results are inconclusive, leaving the paradox unresolved. Yet the most mind-bending solution might lie in holography. If the universe is a hologram, black holes could encode swallowed information on their surfaces, projecting it back outward via Hawking radiation like a cosmic backup drive. String theorists like Leonard Susskind argue this preserves both quantum mechanics and relativity, no firewalls needed. It's as if the black hole isn't destroying the book, but translating it into a language woven into space-time itself, waiting to be decoded. The paradox forces us to confront a humbling truth. Black holes aren't just gravitational monsters. They're cosmic litmus tests for how well we truly understand the fabric of reality. And until we crack their secrets, they'll remain both the universe's most tantalizing shortcuts and its most impenetrable vaults. Humanity has always adapted to new frontiers, evolving thicker skin against the cold, higher lung capacity for mountain peaks, even genetic mutations to digest unfamiliar foods. But interstellar travel demands more than gradual evolution. It requires rewriting our biological playbook to survive journeys where radiation, isolation, and microgravity would break an unmodified body. Imagine crews engineered to hibernate like Arctic ground squirrels, slowing their metabolism to a crawl for years-long stretches between stars, or radiation-resistant tissues woven with extremophile DNA from Deinococcus radiodurans, the bacterium that shrugs off doses of gamma rays lethal to any mammal. Some proposals go further. What if astronauts could photosynthesize like plants, supplementing scarce rations by basking under tailored wavelengths of shipboard light? This isn't just speculative fiction. CRISPR gene editing already allows precise snipping of DNA sequences, while synthetic biology pioneers like Harvard's Church Lab have encoded E. coli with artificial amino acids. The leap to human applications isn't trivial, but the trajectory is clear. Take hibernation. Researchers at the University of Alaska Fairbanks identified the genetic switches that let Arctic ground squirrels drop their body temperature below freezing without cellular damage. Transplanting those mechanisms into humans might require editing thousands of genes, but startups like Suspended Animation Inc. are already testing induced hypothermia for trauma patients, proving the concept isn't pure fantasy. Radiation resistance poses a thornier challenge. Space beyond Earth's magnetosphere bombards travelers with cosmic rays, high-energy particles that shred DNA like confetti. Traditional shielding adds crippling weight, but synthetic biology offers alternatives. Scientists at Johns Hopkins inserted tardigrade genes into human cells, boosting their radiation resistance sixfold. The trade-off: unknown long-term effects. Would crews engineered with foreign DNA still be human in any legal or ethical sense? And photosynthesizing skin, while theoretically possible by splicing chlorophyll producing genes from algae, would demand absurd surface areas to generate meaningful energy. You'd need a sail-like membrane stretching meters wide to power a single hour of brain activity. Yet the most profound obstacle isn't technical, it's psychological. Modified crews might return to an Earth that sees them as outsiders, their very biology marking them as no longer belonging. History offers grim parallels. The Tagish people of the Yukon, adapted over millennia to frigid climates, were decimated by diseases when outsiders arrived. Interstellar hybrids could face ostracization or worse, treated as tools rather than explorers. And what happens when their engineered traits enter the gene pool? A single generation of photosynthesizing settlers could alter human evolution irrevocably. Perhaps the ultimate irony is this: to reach the stars, we might have to stop being human altogether, or at least the humans we've always been. The cosmos doesn't care about our frailties. It demands we change or perish, and that choice between clinging to biology or rewriting it could define our future among the stars. The moment we start splicing tardigrade DNA into human cells or rewriting our biology to photosynthesize, we step onto a razor's edge between evolution and ethical catastrophe. CRISPR precision has made bioengineering almost as straightforward as editing text. Swap a gene here, silence one there, but the consequences ripple far beyond labs. Take the case of He Jiankui, the Chinese scientist who shocked the world in 2018 by creating the first gene-edited babies, altering their DNA to resist HIV. The backlash wasn't just about safety, it was about consent. Those children didn't choose their modifications, and neither might future spacefarers engineered for survival. Are we elevating humanity or creating a new caste of biological tools optimized for labor in the void? Biohackers already blur these lines. Underground labs experiment with DIY CRISPR kits, while groups like Grindfist celebrate implanting magnets into fingertips to sense magnetic fields. If individuals can tweak their biology in garages, what stops corporations or governments from mandating modifications for astronauts? Imagine a mission director arguing that crews need radiation-resistant genes or hibernation adaptations to justify the billions invested in their voyage. The slippery slope here isn't hypothetical histories littered with ideologies that justified altering human bodies for progress, from eugenics to forced sterilization. Yet the counterargument burns just as bright. Every major human leap, agriculture, medicine, industrialization, required reshaping our relationship with biology. Vaccines reprogram immune systems, pacemakers integrate with hearts. Our engineered astronauts so different. The Inuit evolved thicker basal metabolic rates to survive the Arctic. Space is just another extreme environment demanding adaptation. Ethicists like Julian Savulescu argue we have a moral obligation to enhance humans for dangerous missions, calling unmodified crews unjustly vulnerable. In this view, withholding genetic upgrades isn't preserving humanity, it's sentencing explorers to preventable suffering. The debate crescendos when we ask who gets left behind. If only the wealthy can afford enhancements, interstellar travel could become a luxury for the genetically elite. Or worse, what if modified crews can't return to Earth, their new biology incompatible with terrestrial pathogens or gravity? They'd become exiles trapped by their own adaptations. Science fiction has long warned of this divide. Think Gattaca's genetic underclass or The Expanse's belters, physically altered by generations in low gravity. Fiction mirrors our deepest fear, that tampering with biology might not just change how we live, but what we are. Perhaps the most unsettling question isn't whether we can engineer interstellar humans, but whether we'll still recognize them as human when we do. Altering biology redefines identity itself. A crew that hibernates for decades might outlive their unmodified loved ones by centuries. A photosynthetic astronaut could develop a radically different relationship with time, sunlight, even food culture. These aren't just technical hurdles, they're philosophical earthquakes, shaking the foundations of what it means to belong to a species. The stars don't care about our ethics, but they demand we choose. Stay frail and risk oblivion, or evolve and risk losing ourselves in the process. Either way, the decision will echo longer than any voyage written not in the stars but in our very DNA. From bending spacetime with warp drives to seeding the galaxy with self-replicating von Neumann probes, we've ventured into the far reaches of possibility, where science blurs into what feels like magic. Each of these theories isn't just a flight of fancy, they're serious attempts to crack the universe's greatest lock, how to reach the stars within the lifespan of a civilization or even a single human lifetime. Wormholes offer cosmic shortcuts through folded space, while light sails surf on laser beams at a fifth the speed of light. Generation ships turn entire populations into interstellar nomads, and cryogenic sleep pauses biology itself. Then there's the dark forest's chilling warning that the universe might be silent not because life is rare, but because it's hiding. But here's the thrilling part, these aren't just bedtime stories for aspiring astronauts. They're blueprints being sketched in labs, debated in conferences, and tested in simulations. Breakthrough Starshot's laser-powered microprobes could launch within decades. NASA warp drive experiments, though speculative, are probing the edges of known physics. Even the wildest ideas like hacking black holes for energy or rewriting human DNA are grounded in real science, waiting for the right spark of ingenuity. So which theory fires your imagination the most? Is it the elegance of a warp bubble bending reality, or the grim beauty of a generation ship's slow odyssey? Maybe the audacity of turning microbes into interstellar hitchhikers, or the quiet terror of the dark forest's lurking predators? Drop your vote in the comments. We're counting down the most popular picks for a future deep dive. Because that's the real magic here. These ideas aren't just about escaping Earth. They're about proving that humans don't just adapt to the universe, we reshape it. Every wild theory, every failed experiment, every impossible concept is a stepping stone. Someday, a child born today might gaze at Alpha Centauri not as a distant pinprick, but as a destination. And when that day comes, it'll be because we dared to dream bigger than the sky. The stars aren't just points of light, they're invitations, and humanity's greatest chapter is still waiting to be written.